So this is our last, well, no, it's not. It's not. Grignard is our last, just kind of standard synthetic step, do an experiment, make something new, that type of thing. So, this is a very cool reaction. I do have to warn you that this is an experiment that in the past we've had trouble sometimes it not working. Okay. One thing we're going to do that wasn't in the experimental procedure is we are going to flame dry the glassware like we learned last time. We're going to do that with this glassware. We tried that last year and it seemed, I felt like it had success. Oddly enough, it made, and this is what made me decide on flame drying, is that it was never the Monday 8:30 section that had problems. It was always subsequent sections. So what that made me believe is, the Monday section was the morning when it was washing their glassware and there was water on the glassware. And it's the same glassware that the next sections used, and that's why all theirs were failing. So, yeah, let's hope that's the case. Okay. And another thing, there is a recrystallization that we do, which you know because you read it 3 times, maybe 4. And so we do that a lot like the book. We have some variations, like we actually end up teaming up on the recrystallization part and everything like that. And in the past, I've always put all the details for that on the board, sit there, and you sit there watching me write a bunch of details on the board and everything. And this morning I had an epiphany, like, while you guys are doing the reaction, I'm going to be typing it up, so hopefully I get it done. I mean, I have pieces of it, and it's compiling it so that you have written instructions you can follow rather than watching me. I don't think there's a whole lot of utility to it. It's a lot like how you did the recrystallization first semester for the 2-part synthesis. You remember diphenylacetylene. You did a recrystallization in a Craig tube, and you put the spatula in, you twirled the spatula, and vaguely familiar, kind of ish. Okay.
It's a long time ago.
Okay, so we'll see how that goes. I think I can do it. Don't work too fast. No, it's good. Okay, so the chemistry that we're doing involves stuff that I don't think you have. I'm almost positive you haven't had yet. You haven't had. Have you even had aromaticity yet? Discussed aromaticity, aromatic rings. Okay, so you certainly haven't discussed doing electrophilic aromatic substitutions. No. Okay. All right, that's okay. I'll give you the cliff notes, and then when Dr. Horgan does a real nice thorough job and stuff, there'll be a foundation. Okay. We're doing a specific type of electrophilic aromatic substitution. Nitration. Our starting material is methyl benzoate. Electrophilic aromatic substitution, commonly known as EAS. Alright. So we'll do a little EAS intro. When you're first learning organic chemistry, you tend to look at a benzene ring. Draw that up around. You tend to look at a benzene ring as a ring with a bunch of alkenes. Certainly understandable why you would look at it that way. They behave a lot differently than alkenes, so we really sort of don't want you looking at them as a bunch of alkenes on a ring. And very clear evidence of the fact that they don't behave a lot like alkenes is you guys, I believe, yeah, you have learned some alkene chemistry where an alkene acts like a nucleophile, okay, and you have some sort of electrophile. You might have learned MCPBA. Anybody remember that? What does that mean? It's epoxides, potassium permanganate, osmium tetraoxide. I'll stop. Yeah, so where those types of reagents, or bromine is a great example, it's one I'm going to use here in a second. They react with alkenes, and the alkene behaves like a nucleophile. Benzene ring with a lot of those electrophile reagents, electrophilic type reagents, don't react. Okay? And that comes from an inherent stability in that type of system. Okay? Benzene is the easiest, most common example of an aromatic system. That's aromatic. But there are others, and when you get to that point, you'll learn. But right now, a real simple way to be able to identify an aromatic ring is you have a ring, and all around the ring, okay, it's got to be all the atoms involved, there's alternating double bonds. Okay? And kind of an odd fact, which you'll get to later, is the number of alternating double bonds, the number of electrons involved in this, the number of pairs of electrons involved in this aromatic system has to be an odd number. Okay? So there's an example teachers love as the chicky, where it's one. Okay, it's one alternating double bond of spring onion. There's one, or there's three, or there's five, so forth and so on. This is three, right? Make sense? Okay. When you have that type of arrangement, when you have an aromatic an arrangement, there is extra and increased stability due to that. And because of that, they're not as reactive as just a regular isolated alkene. And part of that is something you know, it's resonance, right? These double bonds can resonate around the ring, right? You already do that. Okay. Electrophile. Okay. Will symbolize E+. Okay. That react with alkenes often don't with benzenes. Or aromatic systems. Okay. So this guy, and we added bromine, or that would add across. We did that reaction actually in the two-part synthesis, right? You get NR, no reaction. Okay. All right. However, if you have a really strong electrophile, something incredibly reactive, very electropositive, really looking for electrons, then you can get benzene rings to react. Okay? The net reaction, the initial part of the reaction is addition, just like what alkenes do. It adds. Okay? But when it adds, it breaks. That's the phraseology we use. Breaks aromaticity. You no longer have those three or those odd number of alternating double bonds because one of them went out and added to something. Okay, so it breaks aromaticity in the initial step. But in a subsequent step, it regenerates an aromatic system. Okay, so what it ends up being is a substitution reaction. One of the hydrogens on benzene gets substituted with this super strong electrophile of some kind. All right. But it have very strong E plus, okay? They can react. In a substitution reaction. All right. So I'm going to draw a generic one. I'm going to use a capital E plus, and we don't have an element that's E, okay? But it's just a generic one, so you get the basic idea before we look at some other mechanisms that are hairy and nitty gritty and all that stuff. Okay. All right. So. Benzene ring, somehow or another, and there's lots of different capital E pluses that do this type of chemistry. Okay. The final product is still going to be aromatic, but the E has substituted one of the hydrogens. Okay. All right, so let's look at how that happened. So. When I talk about alkenes, I always say, you know, they can sort of swing open like a gate. Okay, you can think of the double bonds of a benzene ring the same way. All right, and they can swing either way. All right, and they can swing out so that they then become a sigma bond, a single bond to something. Okay, so these electrons here, I'm about to swing them out so they'll become a single bond to something. If they swing out and become a single bond to something, they've abandoned one of the carbons. Okay? So, swings out, attacks that guy. Alright? If one of the carbons gets abandoned by that pi bond, that double bond, what happens to that carbon? Swung out to make a sigma bond to the E plus. What happens to the carbon, that carbon that got abandoned? Has a positive charge. Yeah, it no longer has a complete octet. It only has 6 electrons around it. 1, 2, and the hydrogen that isn't drawn in. All right. So that broke aromaticity. Makes it unhappy. But part of the reason it's willing to do it is it can stabilize this charged intermediate that it's generated through resonance. Okay? So these electrons can hop over here. Okay? Positive charge has moved there. Okay, these electrons can come down here. And in my drawing, the positive charge has moved there. Little refresher about resonance structure. Which one of those is the correct structure of the intermediate? Trick question. They all are. Okay? Or actually, probably a better way to say it, maybe perhaps, is none of them. Okay? The real intermediate is a hybrid of those. Okay? So the real intermediate is some hybrid of the 3 of them that has a partial positive charge up there, a partial positive charge there, and a partial positive charge there. Make sense? All right. Students, when they're trying to do these mechanisms, they often get stuck here, and I feel like part of the reason they get stuck here is is that they forget that there is a hydrogen right there. He's still there at this point. Okay? All right, you've got that hydrogen. Okay? These are not aromatic. Aromaticity gets broken. These are not aromatic. The base comes in. We'll grab that proton. Not sure what base it is, so we'll leave it generic. And then these electrons pop down there, and aromaticity is regenerated. I know my double bonds as drawn here are not in the same location as that. Hopefully that's not bothering me. Okay. All right, make sense, guys? Yeah? Okay. So that's all well and good, nothing too complicated there. The tricky part about this material it's not even that tricky. Like everything in organic chemistry, the individual concepts are not that hard. You guys have probably stayed with me pretty well on this stuff, even though it's brand new to your brains. It's just voluminous. There's a lot of it. Okay? So the next question we have to answer, which opens up a little bit of a box of voluminous material, is what happens if you do this with a benzene ring that's already got something on it. Okay? And we often do that. Benzene rings are very important in synthetic chemistry. They're very important in biochemistry. There's a lot of benzene and aromatic rings in biology. Every one of our DNA base pairs is aromatic. Okay? So it's important to understand this chemistry. It's important to know this chemistry when we're doing synthesis, so forth and so on. So there are some times where we have to do this type of electrophilic aromatic substitution. There's already something on the ring. Okay? And so a big issue that pops right up at that point is, okay, fine. If you've already got something on the ring, where does the new one go? Okay? If you've already got one thing on the benzene ring, there's 5 positions it could go to, right? Where does the new thing go? Okay? That turns out that's an important question to ask, and there's a bunch of stuff to learn. Okay? Where it goes depends on the nature of what's already on the ring. Okay? All right, but before we discuss, if we do section thing here, my librarian glasses. Okay. All right. EAS with substituted in that. We have a system to signify what the different positions are. Okay? It's essentially a naming system, and in fact, it is used in naming of aromatic compounds. Okay. All right. If a substituent already on benzene, okay, we label other positions So I'm going to signify the thing that's originally on the benzene ring with a Greek chi. Okay? Then next it's chi. Alright? So the position right next to it, this is called the ortho position. 2 away from chi is called the meta position. Okay? And this is the para position. Okay? Oh my parakeet. That's how I remembered it 20-some odd years ago. And then on the other side of the ring, same thing. That's also an ortho position, and that's also a para position. All right. And we're going to see that chi, the thing that's already on there, is going to can be broken down into 2 different categories. Okay? One category of chi sends all new electrophiles, all new capital E pluses, to a mixture, okay, of ortho and para positions. Ortho, para. Yes?
When bring up the P, would that be in that?
Oh, yeah, it is. Yeah. Okay. So, there's one class of chi's, and we call those ortho-para directors. They send the new E into typically a mixture of ortho or para positions. Okay? And there's further details that you'll get into later. I mean, sometimes if chi is huge, then things don't tend to go to the physically huge, big. Okay, you get into steric problems, and nothing goes to the ortho position. It'll all go to the para position. But it won't go to the meta position. Okay? Because this particular chi is an OP director, ortho-para director. And then there's another class of chi's, okay, that are all meta directors. Okay? Anybody, just out of curiosity, put you on the spot a little bit, sorry. But anybody from reading the experiment that we're going to do today, what type, the ester that's on the molecule, okay? Is it an ortho-para director or is it a meta director? What position is the new nitro group going to?
Meta.
What's that?
Meta.
It's meta. Yeah, exactly. Very good. Okay, so let's try to understand the groups. How we know if it's an ortho-para director or if it's a meta director, and then we will try to understand why. Okay. All right. So where will new E plus go? Okay. There are 2 types of chi's. Okay? Alright, first type. I'm just going to abbreviate OP, ortho-para directors. They direct the new thing to the ortho-para position. Okay? Alright, so in a generic sense, got some chi, that's an ortho-para director, your E plus. Unless there's some factor like sterics, like what I was talking about. If there isn't, then it's going to get a mix of ortho and para. Okay. All right. And there are also meta directors. of these, you know, yes, it could go to that one, okay, but that's not a different product. Remember, these molecules aren't glued to a whiteboard, they're floating all around, so if I went and drew it in that position, I haven't drawn a different thing. I can just pancake flip that one and come back. Okay. All right, so how the heck are we going to know if you know, if our chi that we deal with is an ortho-para-director or is it a meta-director? Okay. And one of the ways you can do it, and one of the ways some students do it, is to memorize it. Okay. There's a list of the things that can go ortho-para-director, that are ortho-para-directors and meta-directors. You could memorize the two different lists. Okay. But it turns out there are some structural features that can help you distinguish them pretty easily. Okay. The first thing is, if you have a chi that's connected on here, most of the time, not always actually, but a lot of the time there's going to be more than one atom. You know, maybe it's, you know, it could be a whole branch thing and branches off into other stuff. Yeah. Okay. Or maybe it's one atom. But the point is, there's what I call a connecting atom. There's the first, you know, maybe this branch is all over the place, but there's the first atom that connects it to the benzene ring. Okay? And that's what you're going to look at. That's what's going to distinguish these things for the most part, 99% of the time. You look at the connecting atom. What atom connects it to the benzene ring? Makes this sigma bond here. Okay? If that connecting atom has lone pairs on it, it's an ortho-para. Also, in the ortho-para group, just gets slapped on. Have you guys learned about carbocation stability? Things that make carbocations happy? Yes, you have. I know you have. Because we talked about it in elimination chemistry. Okay? Anyway, I was just curious of that. But so anything where the connecting atom has a lone pair, it's going to be an ortho-para-director. And also, like if you have an alkyl group, just kind of a run-of-the-mill alkyl group, isopropyl, t-butyl, you know, could be dodecyl, I mean, you know, 12 carbons long, okay? But it's just a regular alkyl group. There's no heteroatoms, there's no weird bonds, it's just an alkyl group, okay? If you have an alkyl group attached, it's also an ortho-para-director, all right? Okay. All right, so look at that a little bit. How can we identify OPs versus M's in terms of directing? All right. Well, all OP directors, okay, have a lone pair on the connecting atom. Okay. Or chi is a regular, and I know regular is kind of an odd title, regular alkyl group. All right, so what are some of the types of things that could have a lone pair on the connecting